is this a special seminar, I suppose, right? So you guys are all getting off your coursework, and now it's the time to enjoy the research in summer. So I just got Lian's request how to give an impromptu, presentation, and while you present introduction, while you're introducing people, I have to think a little bit about it. But for Xiang, I think I don't need to think about it. He has done so many beautiful work, and as you can see here, and that was graduating from Peking University, major in physics. Even he's right now a chemical engineer, but at his very core, I think it's still a physicist. Peking University has probably not many of you know, but it's a top physics program in China, I would say, right? Yeah, I don't know. Yeah. So he has done. His focus is looking at rheology, I would say. Right. So rheology system, or what they call the soft condensed matter. How the particle interact and change the properties of that suspensions. He has looked at this across a very broad range of different environments. For example, like granular flow. I know that work has got a lot of publicity. He uploaded a video to the YouTube and it got 3 million views in a very short period of time. Is that right? Yeah. So the second one is looking at the stress field. A lot of bacterial work. Was recently one was published in Nature. Now Nature subdivided real Nature. So very beautiful work, and I'll leave the room to you.
Thank you, thank you, Jiarong. Thanks for the introduction. Yeah, we're glad to talk about what we have. As you can see here, we are, as Jiarong said, we are experimental group. We are interested in all different type of fluid motion, especially fluid motion at small spatial scales and fast time scales. I just list some typical pictures we have from our study. So first one is a high-speed photography on drop impact on granular surface. The second one is essentially a fraction force microscopy on drop impact on a soft gel. That by measuring the deformation of the gel, you can measure actually shear stress developed under this very fast spreading event. Third one is look like simulation, as what Lian say. Actually, this is a collaboration between me and Jiarong over 5 years. I don't know. Very long time. This is a very hard experiment to do. This is a real experiment. For the first time, people can measure the 3D flow around a microorganism. So this is essentially from holography that you can track the flow at really tiny scale and how the algae creating 3D flow around itself. And third one, I'm going to talk about later. This is a collective motion of a bacterial turbulence using fluorescent microscopy. And then last, we also have confocal microscopy study coalescence of polymer solution. So yeah, my interest is pretty broad on all different fluid mechanics at different scales. Before I get started, certainly I need to tell you who did the work. So I have 3 graduate students. Deep is sitting there in the center, and Shashank and Zhengyang, they already graduate, and 2 postdocs, Yi and Shuo, they all graduate now, professor in China, and my collaborator Xin Liang and Lauren Francis at the UMN. Is supported by Menli and SF. Okay, so either them or myself, the character of the story I'm going to tell you today. The leading character here is really E. coli, which is probably the most well-studied organism on Earth. So particularly, I'm interested in how E. coli swim. So E. coli has multiple flagellas. In this SEM picture here or TM picture here, you have 4-5 flagellas. So each flagella can rotate, but there's a tiny motor embedded in the cell membrane. This is a really elegant nano machine. The diameter here is only 50 nanometer. It's rotating like step motor and connect to this pretty rigid helical filament through this flexible hook. And the motor can rotate at pretty high speed, 120 Hertz, meaning 1 second rotate 120 times. I cannot do that with my finger. And the motor can rotate in both ways, and rotate either counterclockwise or clockwise, depends on how the protein couple to the rotator or stator outside. Okay, so now when all the motor rotate in the same direction, typically counterclockwise, when you look from behind, those filaments will bundle together into a single helix. By the way, the filament, each filament is very small, it's only 20 nanometer. Typically, you won't see that in optical microscopy because they are too small. And this bundle rotate together, a lot of bacteria moving forward. I'm showing some of the videos from Howard Berg's lab and Harvard. Again, they put some fluorescent label on the flagella. That's why you can see it. Typically, you won't be able to see it. But what happens there, this is a wild study, is that when the bundle rotates, the bacteria will moving forward. This typically lasts about 1 second. But then one of the motor, or maybe a couple motor, will rotate in the clockwise direction. As you can imagine, if all the motor rotate one direction, one motor rotate another direction, this bundle cannot stay. The bundle essentially just open up completely. As you can see here, some of this is like hair just open up. And this makes the body of the cell randomly turn into another random direction. They call this a tumble. Usually this process lasts about 0.1 second, very short. And then all the motor rotate together in the same direction again. They form bundle again. You go back to the wrong phase. There's some very interesting collective dynamics of the flagella here, which I'm not going to talk about too much, but in interest, we just upload an archive paper the end of last year, early this year. Okay, so why they do that? Why they take effort to do this? Because chemotaxis. So if bacteria swim into direction where they see more food, the nutrient gradient go up, then they will elongate the wrong phase, tumble less. So statistically, they will have this bias random motion, and then gradually they will move into the food. That's why this is so important for them. I'm going to use that later in my talk. But another feature, which is less talk about, but certainly people know this, is this what they call wobbling. So as you can imagine, because the flagella coming from random position of the bacterial body, when the bundle form, it's very rarely that the bundle axis will line up with the major axis of the body. There will be always some misalignment. We call that alpha here. When that happens, imagine when you push the bacteria on this side, the body will slide. So even in the wrong phase, you're not going to swim straight. What really happens in 3D is the bacteria actually will run in this helical trajectory, right? It's going forward in this helical shape. And when you do optical microscopy, that's essentially a 2D projection of the 3D motion, you see wobble. As you can see here, this guy, the body, again, this one, you don't see the flagella, you only see the body, you see the body moving like that. Essentially because in 3D is helix, in 2D it's become wobble. And if you look this guy wobbles so badly, it's almost like gyrating, right? It's like rotating. This is when the angle is close to 90 degrees. The whole body just rotates like this, doesn't go forward too much. As I said, people studied this before, but this is another main feature I'm going to talk about later in my talk. Okay, with that preparation, let me tell you the outline. Sure.
This video, in the previous video, we see the flagella.
Yeah.
Right? In this video, we don't see flagella.
Yeah.
Because the challenges of visualizing flagella in this particular swimming.
Yeah, typically when people study locomotion, they don't see flagella because flagella only 20 nanometer. It's way smaller than wavelengths of light. You won't be able to see them unless you put some fluorescent label on the flagella. So you fluorescent microscopy, you can see it. Right. This is a typical video people see all the time when you see swimming of E. coli. Okay, the outline here has 2 parts in my talk. First part, I'm going to talk about bacteria swimming in viscous fluid, complex viscous fluid. This is a single bacterial behavior. And then we'll talk about collective behavior of many bacteria when they're getting very dense. Okay, look, the first one. This is actually motivated by one of my colleagues' work, Ed Kastler. I'm not sure if you know Ed Kastler, very established person in chemical engineering. He retired right before pandemic. In 2004, he asked this very interesting question. Will humans swim faster or slower in syrup? If you're increasing the viscosity of fluid, will humans swim faster or not? Okay, he decided to run some experiment just in the gym in main campus. He has a swimming pool. He filled the swimming pool with water and put some gum powder inside to make a syrup. Okay, viscosity 2 to 3 times higher than water. And he got university professional athlete swim inside and document how fast they swim. Very hard experiment. Experiment itself is hard, right? You can imagine you have swimming pool, you get this powder, dry powder gum. It's very hard to dissolve them. They have to get this really big pump to circulating the water. And after that, it becomes so slippery. Everyone work on that just fall all the time. But what's really hard, of course, then you also have to get permission for human subject experiment, right? You have to ask permission from university to do a human experiment. But this is not the hardest one. The hardest one is after he done the experiment, he has to convince the city of Minneapolis he can dump the swimming pool of syrup into the city drain without causing any environmental issue. Okay, so it's hard experiment. It's worth it. 2005, he got Ig Nobel Prize because of this work. Okay, so before I show the result, Anyone know the result or can guess the result? Will people swim faster or slower in high viscosity fluid? Faster? No answer? Okay. Okay, slower. So let me show you the result. So velocity, normalized velocity in water, no matter whether you do butterfly, backstroke, breaststroke, freestyle, whatever the style you use, the velocity is constant, independent of the viscosity. Essentially, the drag coefficient you get is balanced the inertia you gain you have in higher viscosity fluid. At least in this range, they cancel out well, and they get constant speed. Why this is relevant to our research? Because then someone read the news or report in Nature saying that had Ed Coster done his experiment on swimming bacteria instead of human, he would have recorded much slower times in syrup than in water. The general feeling is that at low Reynolds number, because when people swim, of course, inertia is very important, 10 to the 6, the turbulence, right? But in bacteria swim, the Reynolds number 10 to -6 or 10 to -5. There's no inertia at all. Generally, thinking that if there's no inertia, the only thing you get is just drag, and you should slow down. You can be more quantitative. This, as I showed you before, this is the motor characteristics of flagella motor of E. coli. This is like any typical stepped motor, right? If your motor rotation speed is low, you have a roughly constant torque output. But when you rotate too fast, about 2000 Hertz on natural already, the torque output will go down. And then, of course, you want to determine how fast the flagella rotate. You have the load line. The load line, essentially, the slope here proportional to the viscosity of the fluid. And the cross here determine how fast you rotate. This value should be 120 Hertz, as I showed you before. Now imagine that you're increasing the background viscosity, the load get higher, you rotate, you get more drag. Now, of course, this line go up, the rotation speed goes down. Good thing of low Reynolds number Stokes dynamics that everything's linear. Once your motor rotates slower, your velocity goes down linearly with it. This should go down. Another analogy is that when you go up hills, right? When you go up hills, you have more load. If you have the same torque output from your feet, then you have to slow down. That's essentially the idea they have there. Makes sense. But apparently that guy didn't check the literature. Back to 1670s, last century, someone already measured how bacteria swim in more whiskers, in this case, polymer solutions. They dissolve PVP, which is a water-soluble polymer, and they measured several different types of flagella bacteria, including E. coli, and they plot in the weird way. This, I think, is the old way to show this. They plot this in terms of fluidity, which is 1/4 viscosity. You should read the plot in this way. From right to left, the increasing viscosity. So you can see when increasing viscosity, the bacteria swim speed go up until I go to high velocity or viscosity, a lot of polymer, they start to go down. This is mind-boggling, right? It's not like even human, they keep the same speed. They swim faster in higher viscosity fluid until you have too many polymer, they start to slow down. And after that, there's many work. I only put a subset of that. This is the most recent work. This is Paulo Risha from Penn. They measure velocity of bacteria as function of viscosity. In this case, you see the increasing, and Kim Brown from Brown University, they also show that the speed of bacteria go up when you increasing shear viscosity. Why people still care about this after 670 years? Because this is so important. We know that bacteria never swim in water, although the theory is well developed. In their natural habitat, whether in our body, in soil, in ocean, always non-Newtonian, right? You always has a different type of proteins, DNA, so colloid particles, small soil particles. So everything is non-Newtonian. You really need to understand how they move around in their natural habitat rather than pure water. So that's why this problem will attract a lot of attention. And apparently after 70 years, you must have a lot of theory behind it. So let me list all the major theory existing in the field. The first one is from Howard Berg. Remember the video I showed you? He passed away last December. Very nice guy. Right before he passed away, we asked him a question. He still replied our email. Very established person. Right after the phenomenon found, they proposed some model or picture. They argue that when you have polymer in the system, polymer forming this kind of like mesh network. Bacteria swim to the pore of the mesh network that allow them swim faster. And some Japanese group put this into mathematical formula. They can show that they have speed enhancement. We know this is completely wrong from polymer physics point of view. Because if you have polymer put in water, even they form a mesh, the mesh size should be the size of the radial gyration of the polymer molecule, which is on order of tens of nanometers. Bacteria is 1 micron. There's no way for bacteria to swim through the pore. But Berg is well established. This is still the most cited theory in the field if you go to biomedical research field. The second theory is more recent. If you know those people, Eric Lauga, Julia Newman, Kimborough, they suggest a shear thinning two-fluid model. What happens there is this. Remember, the flagella rotate at 120 hertz really fast. The body rotate at much lower speed because they have to balance the torque. The body is bigger, bulky. Body rotate at 20 hertz. When you rotate something at 120 hertz at 20 nanometer scale, they argue the shear rate near the flagella is so high. It shows shear thinning of polymer solution. We know polymer solution shows shear thinning. When you rotate so fast, near the flagella, you have low viscosity. Near the body, you have high viscosity. They call this a two-fluid model. So even around scale of 1 micron or few micron, you have two fluid around it. Near flagella is low viscosity fluid, near body is high viscosity fluid. From that model, you can show there's a speed enhancement. Next theory, Paul Arisha, Eric Chatafay from Stanford, they argue that when you rotate so fast, you stretch out the polymer molecules. You now start to have viscoelasticity. You have what they call hoop stress. Remember the classical experiment they do with non-Newtonian fluid, you have a rod put in the polymer solution, you rotate the rod, the polymer solution will clamp out, right? It's a rod clamping effect. Same thing here. They argue that near the flagella, you have a hoop stress, normal stress from stretching out polymer molecules, and that can give you the speed enhancement. The most ironic one is from Wilson Pong, Edinburgh. This is really most ironic explanation. They run the experiment using the same PVP from Dow Chemical, although 70 years later, presumably it's a different batch. But nonetheless, they basically get a polymer from the company, they dialase the polymer, get rid of all the small molecular weight contamination, make the size distribution of polymer molecule narrow, and they report that speed enhancement goes down or sometimes goes away. And they argue that the reason why E. coli swim faster is because E. coli eat those small molecular weight contamination, they get more energy and they swim faster. No physical explanation, just basically they eat contamination there, right? They published a PNAS a few years back. This is the existing theory. As you see, there's a lot of established person in the field. They really fight with each other. I'm right, you're wrong, right? When we get started, we're thinking, okay, we want to do something, but we don't want to jump into the fight because at that time I'm going for my promotion. I probably need a letter from those people, right? I don't want to get into the fight. So let's do something different. What haven't been done, which is a bacteria swimming in colloid suspension. Oh, this is a polymer. And I want to study when bacteria swim in hard sphere suspension, what happens. For some people, this is more complicated. For me, from colloid background, I think this is an easier situation. I'm not talking about stretching of molecules. I'm talking about hard sphere, how bacteria interact with that. But it turns out that it can link back to all those models. So the experiment itself is super easy. You just have your colloid particle, you mix with the E. coli, make sure the E. coli concentration is low, they don't talk to each other. Really, you're talking about one E. coli swim through a lot of particles. And you do that in microfluid channel. We vary the size of particle radius from 100 nanometer all the way to 1 micron or 0.5 micron, and the volume fraction from 0 to 20%. This is really limiting by scattering. When you're above 20%, the scattering of light is too strong, you cannot do imaging anymore. When the particle too big, they sediment. You don't have uniform concentration of particle. So that's basically set the upper limit. Let me show you the result. So when you use a 100 nanometer polystyrene particle, PS particle, this is a real size ratio. This is the size of the body, the size of the particle, and we're changing the volume fraction of the particle, increasing concentration particle. We normalize speed by speed in water. By definition, start with at 1. When you add a little bit of particle, in this case, about 2% volume fraction, very small amount of particle, you see about 5% enhance in speed. And then when you add a lot of particle, goes down. Okay, very small amount of speed enhancement. Now we use a 200 nanometer PMA particle, another hard sphere particle. In this case, start with 1. When you go to about 3% volume fraction or 4% volume fraction, get about 50% enhancement, pretty obvious. And then start to go down when you go to higher concentration. The largest particle we use is 1 micron diameter, 500 nanometer radius polystyrene particle. In this case, we see about 80% enhancement, huge enhancement. I want to give you a skill in humans. This is my student Xiang Cheng who ran the experiment. He's a good runner. This is basically his speed versus the world champion speed. In human skill, this is a lot. And you can see that very clearly in the video that is swim faster. Okay. So just summarize what I show you again. Happens at very low volume fraction, less than 4%. You already see this 80% enhancement. So two things. Let me summarize this key result that we see maximal enhancement at very low concentration. And this maximal enhancement depends on size of particle. The larger the particle, the stronger enhancement that you see. You can plot them. The maximal enhancement divided by swimming speed in water, plot the size of the colloid particle, you see an enhancement, right? But what's interesting is that you compare this with the polymer result. In polymer result, you have hydrodynamic radius of the coil as the size of your polymer molecules, and they overlap with our result really well. And this is the difference between Wilson-Pong's result, where he get rid of the small molecular weight contamination, versus the original 70 experiment. Indeed, he see drop, but nevertheless, it collapsed with our trend really well. But this is not the only similarity that you have in this two. Yeah, basically, you have a coil, you ask what is the no slip boundary, because when you have coil, I will actually go that. When you have coil in fluid, when you have fluid pass by the coil, the fluid will never be able to penetrate into the coil. You always has no slip boundary. That's a hydrodynamic radius. Well-defined concept in polymer physics. But this is not the only similarity between the two. Remember, I tell you wobble angle. And there's an anti-correlation between swimming speed and wobble angle. So you see, when my swimming speed go up, my wobble angle goes down. When my swimming speed goes down, my wobble angle go up, which makes sense, right? If you wobble a lot, you cannot go too fast. If you wobble less, more smoothly, you get higher speed. Have anti-correlation between the two. It's almost linear anti-correlation. I'm plotting now directly velocity as function of wobble angle. You see the anti-linear correlation. But then again, how this compared to polymer result? There are only two studies report this. And again, they agree pretty well with each other. The color line is a polymer result. Okay, what else? How about the shape of the trajectory? Without colloid in water, you have this small zigzag trajectory. With colloid, you see the trajectory become longer and smooth. Same thing happens in polymer. Without polymer, this two should be same, although the geometry is slightly different, but that's why their zigzag trajectory a little bit longer. But again, they see zigzag trajectory in water and long, smooth trajectory when you add polymer in. And from that, you can extract a lot of different quantities like rotational diffusivity of the bacteria, mean run time of the bacteria, mean tumble time of bacteria. I just try to convince you that we do all the measurement. This is our result on the top. This is their result in polymer solution. And we plot this as function of volume fraction. They plot this as function of concentration of polymer. But the bottom line is that all the 7 reported swimming features are quantitatively similar in dilute colloid suspension and dilute polymer solution. There's no mathematical proof, but after seeing that, this makes us think that there must be a common underlying mechanism determining the bacterial speed enhancement in both systems. Again, no mathematical proof, but just simply based on the experimental observation. Now, if you believe what I say here, let's use the result here to test all the existing model. Just remind you that we see more than 80% enhancement for volume fraction smaller than 4%, very low volume fraction. This certainly cannot be explained by the Berg's original model, because at 4% volume fraction, the hard superparticle, they don't even touch each other. There's no way they form any network. We know this doesn't work in the first place anyway. The second one is shear thinning. At 4% volume fraction, even Einstein's classical formula for viscosity of suspension still apply. Remember that, right? At a 4 volume fraction percent, the viscosity improve, the enhance of the viscosity only 10%, just based on Einstein's relation. So let's say you shear thinning, you get rid of all this actual 10% viscosity, you have water, purely water, near your flagella. This is far enough to explain the 80% enhancement. A 2-week shear thinning effect for this explanation. Normal stress difference. Our particle, PSPMA, really hard sphere particle, the modulus is 2 to 4 gigapascal. There's no way that small molecule small flagella rotation can deform this particle. So there's no hoop stress in the system either. Of course, we wash our particle very carefully, make sure there's no contamination. And then I'm stupid enough, I'm still trying to search literature whether bacteria can eat PS or PMA. And then my colleague tell me that if they can, then there's no issue of microplastics in our ocean. Everything will be degraded by far, right? There's no way that it can metabolize PS and PMA. So now the theory really works if you believe they have a common origin. So we destroy all the model. Now we have to provide something that we believe is the reason. Again, it's I would say one of the model, okay? So the idea is pretty simple. If you have a particle, you drag a particle with some force to the right, of course, your particle will move to the right, no matter whether high Reynolds number, low Reynolds number. A low Reynolds number, of course, is a classical Stokes law, right? 6 pi eta A V. But now imagine you have particle next to a stationary wall. Even you drag particle only horizontally to the left or to the right, your particle has to rotate in order to satisfy no slip boundary condition between the two gaps, between the gap, in the narrow gap there, right? So particle you have to rotate. People call this as a boundary induced torque. Not real torque, just because you're next to a boundary, you have to rotate. Now we argue that same thing happens when bacteria swim next to a particle. The D here can be really small. Based on some study before, the D can go down to 50 nanometer. So your bacteria now moving vertically upward, but because next to this hard particle, the body will feel this boundary induced torque will bend it toward the particle. You get this tau B. And you can calculate tau B based on lubrication approximation. Again, because D, 50 nanometer here is much smaller than the size of the body and smaller than the size of particle. So you can have this very kind of elegant formula from lubrication theory. The important parameter here is the gamma, which is size ratio of particle over bacterial size. But bacterial size is fixed at 1 micron. So essentially just the size of the particle. That's this one. You have logarithmic dependence because it's from lubrication calculation. Okay, so we know that a low Reynolds number, you shouldn't have a negative torque, right? All the torque has to be balanced because there's no inertia. What balances torque? We argue that the torque is balanced by the bending of flagella hook. Remember the flagella linked to the motor by this very flexible hook. We argue that the hook essentially behaves like a spring. There's some equilibrium angle, which is the angle before bacteria touch or near the particle. And there's a new angle, which is deviated from that equilibrium angle. And K here is essentially the bending stiffness of this hook. And we argue that this torque balances that torque. Because again, you have to have a zero torque in this situation at low Reynolds number. When you have that, now you get relation between wobble angle and the size of particles. Now the first step we do is we just take experimental result. Remember, I have this anti-linear correlation between wobble angle and velocity. If I just fit it, get a fit line, now I can turn wobble angle into velocity. Now I get a relation between velocity and size of my particle. There's only one fitting parameter, which is the bending stiffness of the hook. So I fit my result, I can get pretty good fitting. So there's a black line there. And the stiffness we got is 7 times 10 to the 10 to negative 19 Newton meter. And Howard Berg measured this a long time ago using optical tweezers, bending the hook. They got 5 times 10 to negative 19, order magnitude. So they match pretty well. And let's go to general question, why polymer also works well. Because we know that if you have a polymer coil in a fluid, you will never have, or very rarely have the case that water can penetrate through the coil without any resistance. This is essentially the completely draining case. This is the base of the Ross model. We know that if you have a single molecule, you have to use the Zim model to explain the viscoelasticity or the rheology behavior of dilute polymer solution. In this Zim model case, essentially you have a non-draining case. When you have flow around the coil, the flow always passes around the coil, and with no slip boundary condition here determined by this hydrodynamic radius. So that's why the explanation also applies for coils if you replace the size of particle to the hydrodynamic radius of the coil. And this is a classical thing again in polymer physics. So the last question, I will go very quick. It's a minor thing. So we now use this empirical fitting. Can you also predict this with some model? Predict how the wobble angle changes with the velocity. is intuitively very easy, right? Because if you wobble a lot, you do not go fast. If you wobble less, you go faster. But to build a model, it's simple but tedious. You have to align, sign the angle here, alpha, the misaligned angle between the bundle and the body. You have body rotation, you have flagella rotation. Then the whole thing has to rotate in order to balance the torque. That's what we call omega cm. Essentially, then you can write out the kinematics of the body, kinematics of the bundle, and then you write, this is a simplification, right? You write basically the force on the body and force on flagella, assuming there's no hydrodynamic coupling between the two, except that the force has to be equal, the torque has to be equal to get torque-free and the force-free condition. This is what they call Purcell model for E. coli. So after you do that, I will skip all the math, it's just some tedious linear math, right? Not like Navier-Stokes equation, non-linear, you cannot solve. This one you can solve easily. So you can get velocity and omega, and this is basically the result, no fitting parameter. Actually, it's not perfectly linear. It's anti-correlated, but not linear. Okay, we can get this result. Okay, let me summarize the key part of the first part of my talk. Basically, experimentally, I show you there's a common origin of two phenomena. And then we argue that it's very important to consider colloid nature of complex fluid. So far, all the existing models study bacteria swimming in complex fluid. They always treat complex fluid as continuum medium. They have non-Newtonian constitutive equation, shear thickening, whatever you have, viscoelasticity. But what we argue that to understand how bacteria swim, you cannot treat the complex fluid medium as continuum. You really have to consider each individual molecule, how that interact with bacteria through Newtonian fluid. If you consider that, you can get your answer for what happens. And also we get a model for bacterial wobbling, which is the minor thing we got. And I think if you want to take home message, someone read the news and views for us in the company with the article. And this is one thing you just need to remember. Very nice. It's not from us, from those people. So the idea is that when bacteria away from particle is wobble a lot, has this big radius of helix trajectory. But when bacteria next to the particle, it wobble less, you become more straight, you swim faster. If you keep doing this, you see one particle, see another particle, see third particle, you continue doing that, on average, you get higher speed. And that's it. That's all the story I'm trying to tell you. Yes. Sure. Yeah, go ahead.
You don't need to look at me.
So what's interesting is that there's a peak velocity at relatively low concentration. Oh, sorry. Thank you. So there's a non-monotonic dependence on concentration. So can you explain, or at least qualitatively explain, why or what is that maximum optimal concentration and why it goes
Very
down?
good question. So when you're next to the particle, your hook get bended. When you're swimming away from the particle, your hook will gradually relax back to the equilibrium position. And this is coming from the viscous drag, balance the motion of this. So before you fully recover, if you can see the next particle, you can have the keep enhancement. We do order magnitude analysis. The distance between two particles can predict the peak concentration. Yeah, basically, what's the time scale need for this to relax back to the original location? This time scale, you can then calculate the distance between particles because you know how fast bacteria swim. And this distance gave you concentration that predict the peak concentration. Again, we just do back envelope calculation. And you see there are a lot of things you can do with this, because right now, the calculation we do is just you by hand, put the particle there, put bacteria there, ask what's the force. But in reality, much more complicated than that. Before your bacteria really touch the particle, the flow already drag the particle moving around. We have, again, hand-wavy argument from the flow nature that actually this far field flow can drag the particle to the direction where the bacteria can nicely interact with the particle. But again, you need a lot of simulation in order to see that. There's no analytical solution for those things. Yes?
I don't know about coli. Our experience with motile. Thank you. Our experience with the motile green algae. They have two flagella.
Yep.
And these flagella, they can oscillate with different frequency.
Yes.
They can also change the plane of oscillation.
Yep.
So if there is a mismatch in these two, that generates net torque and tumbling of the cells.
Yep.
And it turns out that a very important parameter is what is the distance between the flagella and the center of body mass.
Yes.
Now, in your case, you have several flagella at the backside of the cell. And these flagella, they obviously they have a different distance from the body to some common center. And I assume that these flagella individually can have different oscillation frequency. And presumably they can also have a different plane of oscillation. So, and I like you simplified using just one flagella in your sketches. So did anybody investigate the simultaneous collective motion of these flagella?
It's a very good question, and certainly a big question in the field, right? So they have to collectively rotate together.
Mhm.
So right now, the general consensus is that they form a bundle,
Yeah.
and the bundle is pretty tight.
Yeah.
So because the filament is only 20 nanometer in thickness, the distance between bundle, the filament in the bundle will be smaller than that. So it's a pretty tight bundle. We just have, as I mentioned, that archive paper we're trying to submit right now, or submit, get rejected. We're trying to resubmit it. So we talk about collective dynamics of flagellas. So how the collective dynamic flagella influence swimming speed. Yeah, there's very complicated because you're right. There also the case as what you mentioned, because the body is here, the flagella coming from all different directions, right? There also, when the flagella rotates, it has to interact with the body. There's some actual dissipation due to that. And also in the bundle, they are not soldered together as a solid bundle. They also have some relative motion. And our recent paper showed that this relative motion of filament in this tight bundle is very important in order to understand how they swim.
And
in this, you're right, in this model here right now, we just use the common, consensus saying that this is a single bundle, but in reality that, yeah, the collective dynamics of filaments play a big role.
And there is also another interesting phenomena that we observed with motile algae is when you are looking at flagella, even with high-speed holography, they may appear stationary. They may appear that they don't rotate. However, if there is a fluid motion around the organism, they can use that rotation to counteract the rotation of the fluid motion. So, and that is inducing net propelling of the cells. So, for example, if you have a simple shear flow between two parallel plates, if you look at the flagella, they don't rotate, and cells go with an angle of 45 degrees. That will be the angle of principal axis in a shear flow. Doesn't mean that they don't rotate. They are simply riding on the shear of the flow.
Yes.
So that's another possibility that they may explore.
Yeah, there's some extension you can do with what happens in the shear flow, right? I mean, there are already some study on E. coli apparently in shear flow, how they interact with the big walls under shear, stuff like that.
Thank you.
Thanks. Okay, so let me go to the next one quickly.
Quick question.
Oh, sure.
Looks like in that schematic, the particle is a lot bigger than the bacteria.
Yeah.
Right. In reality, in your experiments, I think the particles are kind of the smaller, right?
Yeah,
a little smaller than bacteria.
Yeah. The smallest one we use 100 nanometer, small, but for 100 nanometer, you don't see much of a speed enhancement.
Right.
Only when it's large enough, you see strong enhancement.
Yeah.
Right.
I was just wondering if you extrapolate this, would that mean if you have bacteria swimming in a very small channel, like, or even the interstitial flows regions in the pros media, they will actually have a faster speed?
You will have an effect that their wobble will reduce. When the wobble reduce, certainly it will have a higher speed. But on the other hand, if you think about the tube, they swim in the tube, there are a lot of hydrodynamic drag from the walls surrounding the body. And that's another effect that we don't have here, right? We only have basically interaction on the side. But if you're talking about everything surrounded by solid wall, that's another thing. But people do see some, if you have a soft, deformable wall, when bacteria swim through, it will get higher speed. Yes, they will swim faster inside.
Okay.
And there's some study on how the confinement, actually, yeah, you point out a very good effect. People know that actually, if you have confinement effect, they will swim faster, the bottom line. Yeah.
All right, thank you.
Yep. Okay, so when I present that, then a lot of people, I don't get a question so far, but I assume you may have the question. What if you have a bacteria interacts with the bacteria, not a bacteria interacts with particle? if you have active particle, what happens? This is someone else study. You can see that they highlight two. When bacteria come together, they actually collectively swim together, right? I mean, this is two, but there's many. There's another pair. Actually, they swim together, right? There will be more interesting phenomena if it's two particles, they all swim, right? So what I'm interested in what happens when you go to really high concentration, not only two particles, but a lot of E. coli. And here's what you see. Very beautiful picture. And this is a real-time video of what happens when you have a high density of E. coli. And this is the field here from this direction to that direction, about 400 microns, 350 microns, something like that. Each of the black and white dot, they are single E. coli, depends on whether they're in focus or out of focus. And you can clearly see from behind, there's a jetting, swarming structure, right? It's really like a Starry Night Van Gogh painting if you freeze it, right? So this is like fish schooling or bird flocking, right? And also, I'm sure for the audience here, natural response to that, this looks like a turbulence flow, although turbulence happens 10 to the 6 or higher. This one, for single bacteria, 10 to the -5. And actually, people call this a bacterial turbulence or active turbulence. There's many work on this recently, very hot topic. Okay, so it's a very interesting study how they collect the swim. I'm show you some of the results we have, and then at the end I will post the open question our group is working on right now. Just give you kind of overall view of what we have. So the first question we address here is that how they form this turbulent structure. We know that at low density, you see this video from Berg's group, they are randomly swimming, but the increasing density, at a certain point, they start to show this collective bird flocking, fish schooling type of behavior. How this happens? To address that question, we make a genetic engineer of E. coli. Our E. coli typically live on gut, they don't care about whether it's bright or dark. But we design this E. coli, they can respond to light. When we're changing light, in this case, changing the voltage on the light bulb, you can see when you're increasing light intensity, the swimming speed go up. So we can control their swimming speed. And their response is pretty fast. When you're changing from 3 volt to 9 volt, within 1 second, you can see the change of the swimming speed. It's a very nice string. Now, I put this string in a suspension. First start without metal light or with a red light, they are not sensitive to. And of course, everything is stationary. You only have Bounding motion of particles. That's what happens at t equal to 0. Now I turn on the light at time t equal to 0. We can see gradually how this turbulent structure form as function of time. That's what you're going to see here. So as time goes in second, you can see how this turbulent structure set in. The arrow there is just PIV flow. Okay, now we can see really the kinematic of this transition from non-turbulence to turbulence.
So that was like the full distribution of the lights everywhere.
Yes.
Okay.
Yeah.
Everything kind of just took off in the direction it was originally facing.
No, it's a uniform dark and big. Yeah, they start to come together, you know, start to form a collective behavior. From that, you can build up a phase diagram. So 3 control parameters. The first one, actually, we also vary the fraction of swimmers. We mix swimming E. coli with non-swimming E. coli. F equal to 1 means 100% swimming. 0 means that all of them is an immotile bacteria. X-axis here, swimming speed, changing controlled by light. And of course, this one here is density of concentration of bacteria. And the black dot is random swimming, and the red circle is the turbulence. And if you're interested, I can tell you the detail how we determine the boundary. But you can see here, when you have higher swimming speed, more motile bacteria, and higher density, which give you this corner here, you see a turbulence flow. But when you have the opposite trend, or opposite control parameter, you see a random swimming. You can see the transition between the two by controlling those parameter. Then can we determine this boundary, the phase boundary? To determine that, you have to understand what's flow bacteria generate. And this is, again, classical theory. There's no force on the bacteria, as I used many times already, force-free condition. And if you have a force on the body, a force on flagella, this two force has to be same. So in the far field, it has to be force dipole, and force dipole go as 1 over r squared, right? Decay in the power law case. So we know that flow generated by bacteria nearby should be force dipole flow, and this has been confirmed in experiment, but only in 2D. That's why the 3D flow measurement is really important. So far, we haven't done that for E. coli, but we have to do that for the green algae. But this someone's a 2D projection measurement. for the swimming flow field around single E. coli, and it's confirmed the dipole flow when you're far away from the swimmer. Now let's use this to calculate. So here's what I'm calculating. I'm considered an encounter event of 2 bacteria. Now, 1 bacteria here, 1 bacteria here, this bacteria swim by. When this bacteria swim by, you will have a flow exert on this neighbor bacteria, right? The flow here, we know it's a forced dipole. Then we can ask, in this forced dipole flow, how much does the bacteria rotate? And we calculate delta theta, we calculate delta theta square. This gives you this dipole contribution. Kappa here is dipole strength. But also because this bacteria has dipole flow, is applied to this bacteria, but this bacteria has finite size, rigid finite size, will modify that flow field. And that modified flow field will have a reflection flow on the bacteria itself. So this is basically the higher contribution. This is reflection flow contribution. You can do even higher order, but go to higher order, contribution gets smaller and smaller. So basically this is saying that if I have 2 bacteria encounter over time scale of tau, how much rotation I will have just from fluid. But also bacteria has its own random motions, right? People measure this random diffusions and they have an effective rotational diffusion coefficient, dr, 4 times tau give you delta theta square. Our hand-wavy or simplified model is to argue that at this critical distance, the delta theta square from hydrodynamics will be same as delta theta square from random motion. This gives you a critical radius or critical concentration. If you are below this radius or higher than this concentration, hydrodynamics will win out. You should have a collective swimming due to hydrodynamics. However, if you are larger than this distance, smaller than this concentration, random diffusion will win out. You have random swimming. So again, hand-wavy type of argument. Based on that, you can predict how does the critical concentration change with swimming speed, fraction of swimmer, as well as the kappa, essentially the dipole strength, which depends on the natural swimming speed of bacteria, isolated bacteria in 1 bacteria swimming speed. And using that, actually, you can have pretty good prediction. This is our model prediction. Simple here is a phase boundary that I showed you earlier on. And of course, you can argue that you only consider 2 bacteria. There are many other bacteria, and also you didn't show this collective behavior from hydrodynamic interaction. Someone has done that. I'm not a theorist, so never go to those complicated derivation. There's a mean field theory from Don Koch at Cornell University and Mike Shelley from NYU. They also do the similar calculation, and this is the prediction of more complicated model. That's actually also agree with the boundary that we see. Okay, so yeah, so actually I already showed the surface here. This surface actually is a prediction from those theory, from our theory. So you can see the 3D agreement between our experiment and the theory. Okay, with the last 5 minutes, I want to talk to you a big question that puzzled us a long time, and we're still working on that. So I don't know the answer for this, right? This is an open question. So I use the analogy of bird flocking and fish schooling. And that's actually a general impression of the field. When people think about bacteria flocking or this active turbulence, they think about bird or fish. This Astor's famous painting, right? Now, if you look at all the literature, the review article on active matter, they always list swimming bacteria in the bulk as polar wide system. Wide means it's a suspension. It's not like a dry granular medium. There's the active matter in dry granular medium. So wide is clearly unambiguous, but they always put the bacteria in a polar system. Polar means that bacteria will line up head to head, tail to tail. Okay, but this is the question that we want to challenge. Yes, you have a polar particle, that's for sure, because the head and the flagella is very different, it's bulky and thin, and bacteria swim this way. But polar particle can align polarly, but it can also align nematically. There's no reason that a polar particle must align polarly. Our impression that bacteria align this way, essentially from bird or fish. Of course, bird or fish, you see that they all swim in the same way. Their heads are going to the same direction. But for bacteria, actually, no one really look into that. They just get enforced by macroscopic model and saying that bacteria is like that. But we train that it's not very clear how they align. So what is existing experimental evidence? A lot of this from our own study. So at least 4 evidence, existing evidence. The The first evidence you could argue that if they align nematically, you should get a 1/2 defect. It's like a liquid crystal. This 1/2 defect only happens when you do not distinguish what's head, what's tail. If you distinguish head and tail, this is not possible. You get a positive, negative 1 defect. But as I show you in the flow here, this is really like turbulence flow. It's not like liquid crystal structure, because a small aspect ratio bacteria, very large swimming speed and 3D flow you have here, is very hard to tell what type of defect structure you have. And actually, it's kind of strange to ask what's the defect you have in turbulence, right? So this is not conclusive. How about macroscopic flow or the phase diagram? The phase diagram I will already show you. Our model can predict the phase diagram well. And remember, in predicting this phase diagram, the only thing we need is that bacteria far field the force dipole. And this force dipole does not depend on which head was the tail. We just need 2 forces equal and point to the opposite direction. And this is the perfectly symmetric far field with respect to head and tail. So you don't need a polar structure. You only need nematic structure to have this prediction on the phase boundary. How about the structure of the flow? So this is something we did through several studies. The first study we study is what's the correlation length of this turbulence structure, right? You have this vertex, what size of this vertex? And we measure that at using this colloid geometry, essentially the 2 gap. We can change in the gap thickness h, and we measure how big of the vertex. And turn out that the vertex size increased linearly with the gap thickness. Seems that the larger the system, the larger the vertex you have in the system. Just a side note that actually this also happens in bird flock. And there's some, I'm not going to there because there's a lot of controversy here. A biological system pose at a criticality because when you have power law relation, length scale depends on system size, there's a critical phenomenon associated with physics. But I'm not talking about that. So this is a side note that bird flock shows a similar feature. So first, that you get this length scale increasing with system size. Second thing is that, I'm sure that I don't need to introduce the concept in turbulence, everyone use that. You can measure the energy spectrum, right? You get point-point velocity correlation, you do Fourier series, so that you get E of K. And we get some scaling. This is not a Kolmogorov famous scaling because it's active turbulence. You see at large K, you get -3 scaling, at small K, you get most light scaling. And this 2 feature has been predicted by active nematic fluid theory. The theory predict, again, from Dunkirk and Mike Shelley, what they predict is that the most unstable mode is when K equal to 0. That means that the longest wavelength is always the most unstable one. And of course, the longest wavelength you have in your system is the system size. That's why the system size will determine the correlation length of your system. And more interestingly, very recent paper, they found that there's some universal energy scaling for active nematic fluid, and their prediction is in 3D, the scaling here should be -3 and 0. That's same as what we see here. Okay, how about active polar fluid theory? There's also, this is the most established active polar fluid theory. It looks like this is incompressible. This looks very like, very similar to Navier-Stokes equation, except that you have this extra term that allow you to generate polar structure, and there's a higher derivative for velocity. In any case, for this theory, they show there's an intrinsic length scale that's independent of system size. And also, if you measure the energy spectrum, they actually see the peak, but this peak actually is determined by the confinement of the system. And lastly, density fluctuation. This is our picture. Use light shining through the system. You can see the region that's the black region that's light. The darker region apparently have more bacteria there. The lighter region there has a lower bacterial density. And you can calculate the density fluctuation as function of size of your system. You can see this fluctuation is much larger than square root of n, which is what you believe what you expect to have when you have central limit theorem. But apparently the system break that when you go to smaller enough size. So this giant number fluctuation can only happen when you have a polar fluid, non-nematic fluid. Now, the conclusion here is this. Again, open question, I don't know what's the answer. The full evidence that we have so far, defect structure very hard to tell. Due to bacterial turbulence, macroscopic flow structure saying that you only need nematic structure in your system to generate those features. But density fluctuation point out that maybe the system is polar. So exactly how much polar component you have, how much nematic component you have, that's still open question. So even for the classical active fluid, We still don't know what is the orientational symmetry in the system. That's the open question we want to address, or we are addressing right now in the group. Okay, with that, I think I will end my talk talking about two things. The first thing I'm talking about single bacteria swimming in a viscous complex fluid. And the second, we're talking about collective behavior. And we show you that the root to active turbulence is really coming from hydrodynamics. Based on hydrodynamics alone, we can predict the phase boundary. And I should put a question mark here. What is the original symmetry of bacterial turbulence? Still open question. Okay, thanks for your attention. I should mention that the cover is designed by Deep. It's sitting there. So. Yes.
By the bacteria, is it with 2D turbulence or 3D turbulence? Because the fact that the scale of the vortex tend to approach the scale of the system suggests a 2D turbulence type of behavior.
So
and
I'm not sure. Okay, so I'm not sure if I understand the question or I can answer the question. So I can tell you how we do the experiment, right? So we have a co-ed geometry. I have two parallel plates. We just put our bacterial suspension inside. We're imaging at center of the cell. We're also imaging at different layers actually. And we see just turbulent structure within the layer that we have.
yeah.
I'm not sure whether that's a 2D turbulence or 3D turbulence. How to
Because the
answer
2D turbulence has, you don't have any vortex stretching and you have an inverse cascade.
Yes.
So the scale grows. So I think there are some prediction.
Maybe actually you can think about in this system, the energy injection is from the local scale. It's from single bacteria.
Right.
They're swimming, creating the
So
turbulence.
that's why I was thinking it could be interpreted within a 2D turbulence flow, but that means that you can compare with the results from soap films with all kind of different type of
Sure. Yeah, there's some study, as I mentioned, that this recent paper they call universal energy scaling. They thinking about this energy, how the energy cascade happens from smaller scale to larger scale. And I cannot remember detail. The conclusion is that they are not like classical turbulence. And this is not surprising they are not like, because they are not turbulence, right? So there's some degree, how the cascade happens, how the larger scale propagating smaller scale energy propagate to larger scale. They claim that this propagation is different from classical turbulence.
Yeah, the 2D turbulence, entropy dynamics is different, the cascade dynamics is different. So that could be one way to
Could be.
Yeah. Thank you.
So you got that was amazing work, by the way.
Thank you.
I thought it was great. You got maximum performance at 3, 4, 5% solutions. How's that relate to biological fluids that the E. coli would typically be in? Have they evolved to maximize their performance in fluids that they want to exist in? Or
very good question. I cannot answer. We're always trying to say something about biological significance. It never fire out well. We always get rejected because we are not biologists. Whatever we argue, the reviewer said this is not true. So we stick to the fluid mechanics part. We just see what we see and provide hydrodynamics interpretation of what we see, explanation. Whether there's a biological significance, whether evolution goes in that direction, I would say that's an open question, at least for us. This is a fate of a recent paper. We're trying to motivate the paper by biological significance, just get killed. Apparently, we do not speak the language of biologists. That's the big issue, that you don't know what the answer you provide is sufficient supported or not. But fluid mechanics, I'm very confident. And from fluid mechanics point of view, we propose this is the reason why that happens. But it's a good question. I think naturally we'll think that, right? Because they have maximum swim speed, maybe they want to go there because their natural environment has something like that. But on the other hand, it could be just coincidence. There's no, at least we do not have any evidence for either way. Yes.
Very nice work. But I suggest you switch to algae instead of E. coli.
Yes.
No, don't go there.
Yeah. The reason why algae is that they do not flock. They are not happy when they are not, let me just go there. They are not happy when they go to high density. They just too crowded and they stop swimming.
Yeah.
But as I mentioned early on, this is the work that I have with Jiarong over 5 years. But this one's on single algae, and this is a sea clammy. You probably know really well.
Or chlamydomonas.
This is, yeah, this is a clammy. And what this happens that we put a very small tracer particle around this swimmer, and we're trying to use holography to document the 3D flow.
But I wanted to ask you the following question. Theory advocates that below Kolmogorov scale or Bachelor scale, turbulence has no effect on microscopic
Yes.
organisms.
For sure, yeah.
And well, if you decide to work with algae, we can run a simple experiment. Put algae or even bacteria in a turbulent flow versus non-turbulent flow. What you will see very significant difference in metabolic activities, where microorganisms will significantly uptake more nutrients than in a turbulent flow than in non-turbulent.
Yes.
So if you go with a standard theory, you can say.
Yeah, it's diffusion, right? Locally, it's always a low Reynolds number.
Scales, there is no any fluctuation.
Yeah.
It should not make it.
Yeah.
And so is there any hope that somebody, and I believe the reason is, one of the reasons is because below the scales flow is not steady.
Yeah.
It is unsteady flow. So the whole idea of the Kolmogorov scale is a steady state conceptual approach.
Sure, it could be the case. Yeah, I mean, I do know some of the study that they show that turbulence actually make difference, right?
Yes.
Although at smaller scale, really at micron scale, you should always diffusion dominant everything, right? The transport shouldn't play any role. That's one thing that when those type of active turbulence first be founded, actually, I may go to the bigger one. You can see some kind of dust particle we accidentally get into our system. They diffuse much stronger in this active turbulence flow. And one argument, again, that's related to biological significance, whether they do that because of this. So you can see later, you see here, there's some dust particle actually trapped in there. And they measure the diffusion of those dust particle. Of course, the diffusion enhanced thousands-fold, right? They're saying that, okay, now I have this active turbulence at so small scale, this help the diffusion particle because normal turbulence won't do anything at this scale. So only because this is swimming of bacteria make them diffuse faster. And the goal is that then they can maybe see the food particle faster because diffusion is enhanced.
Thank you.
Yeah.
Thank
But apparently right now people know that even turbulence will have some effect at the small scales. Yeah.
Thank you.
Yeah.
Yeah, very interesting work. So I just have two questions. The first question is about in the first example where you show individual bacteria swimming, and so you contrast your theory with other people's theory that based on continuum assumption, right? So in the second one, it's more like a continuum system if you think about it from turbulence perspective. So when I was looking at your spectrum scaling, I think you're getting like -3 scaling instead of typical classic turbulence minus 5/3. So that scaling looks like elastic turbulence scaling. I don't know whether you have compared with that.
I haven't. Yes, they all there are no non-classical turbulence structure.
Right.
I don't know what's the energy scale. I'm sure someone measured that.
Yeah, my recollection is about -3 or -3.5, means somewhere in between that. So in that case, they treat the system as non-Newtonian fluid like polymer solutions and like elastic turbulence. I think there may be, of thinking going back to continuum, system and to get a better interpretation of the results, right?
This system actually has very interesting rheological feature. Viscoelasticity, they may have a little bit of viscoelasticity, but you measure the viscosity of this. You just put those things, the swarming thing in the rheometer, you start to shear, you measure zero viscosity. So basically means that you have parallel plate, you move the top plate, the bottom plate does not feel any motion from top. They call this a bacterial superfluid. This is a very interesting rheological features from this system. And there's tons of study on that too. So
So my second question is about your final question, that the polar and pneumatic, assumptions. So if these two bacteria sort of swim in the pneumatic way, do you think the rotation of the bundles is in the opposite direction? Is that right?
No, they all swim. Individual bacteria, they swim in the same way, meaning that the bundle always rotate counterclockwise if you look from behind.
Right.
Because one swim this way, one swim that way.
Right.
Then, of course, there's a kinematic effect. Let's say if my and my neighbor all swim together, we'll stay there for longer time.
Right.
But if I'm swimming this way, then me and my neighbor will separate very quickly.
Do you think that, if this is in opposite direction, would that this cause entanglement of this, two bundles, or the kind of the?
I don't think in this case, well, I mean,
whether-
even though it looks dense, actually the volume fraction here is about 8% in this one. So there's still plenty of space. I mean, if you think, because they are rod, right? They are elongated. If you rotate this rod, then you go way beyond the semi-dilute regime.
Mhm.
But if you're thinking about just rod, there's still a lot of spacing between them.
Okay.
But your question actually is interesting that not this type of bacteria, but single flagella bacteria, not multiflagella. Multiflagella will never see that. Single flagella bacteria, very occasionally we can see when two swimmers come together, their bundle actually, their flagella from two different bacteria, they form bundle together, they dance together, but that's very rare. We only see one time or twice.
Yeah.
And that's a very interesting question.
Yeah, I'm just saying maybe it's interesting to look at, this different swimming, different assumptions and polar versus pneumatic, to look at the bundle kinematics and then see.
I mean, I push deep, he's there. To look at the bundle in this case, I think the answer so far is impossible, right? Or close to impossible. We're trying hard to do that because even the Howard Berg's picture I showed early on, where they put the fluorescent label, they see flagella.
Mhm.
It looks beautiful, but that's why we contact Berg just right before he passed away. He basically saying that those pictures, videos is one of, 100. You have to keep trying until you get good day that you get very nice picture. And you put the flagella label in this type of high density turbulent flow is hopeless to see where is the flagella located.
Right.
It's just
But
so
in
hard
the
to-
first video, I noticed you showed there's two bacteria just
Oh, yeah,
going
that
parallel
one,
in those cases, right?
Those in principle you can, yes.
Yeah, if you break down this into individual
Yeah,
cases, you
yeah.
might be able to look at that.
Yeah, that's a good question. Yeah,
yeah,
good suggestion.
yeah.
Yeah, for single two, you can in principle do something there. Yeah.
All right. Any other questions?
Anyone? Well, I have a question. So for the last part, you show the equation showing, to describe the active turbulence. How good is that equation?
What do you mean? How good?
Basically, let's say I'm trying to make an analogy for an S equation. Okay, and an S equation is good.
Yeah.
Okay, it's just hard to solve, but the equation itself is accurate.
Yeah.
And if one can simulate it using computer simulations accurately, one will get a good description of the turbulence field.
Yep.
If one can do good theoretical analysis, one can have a good answer. So my question is for this equation, like basically if whether or not, it has.
Very good question. So these two work, the original PNS and PR work, they simulate this numerically, they can see turbulence. And that's why they claim that this one can explain the bacterial turbulence. Mm-hmm. But I think there are a lot of questions right now about this length scale. So this length scale essentially insert by hand into the equation itself. That's why the equation has an intrinsic length scale.
Mhm.
But at least we know from our experiment that when you're changing system size, this length scale change with it.
I see.
So there's no intrinsic length scale, at least in our experiment. So, but the equation itself is beautiful, right? I mean, you have Navier-Stokes type of term, and then you have, this is really like a Landau, free energy term, right? This allow you to have a phase transition when alpha beta ratio is large enough that you get a polar alignment. So it's really combined. And then they have a microscopic model can show that when you co-screening the microscopic model, I think this is a PRE paper, you co-screen the alignment, you can actually get this type of equation from the microscopic model. Yeah.
Great.
Yeah. Thank you.
Well, if there's no other questions, let's thank Professor Xiang Cheng for giving us such a wonderful talk to kick off our summer. Yeah. And also, I want you to give a round of applause to our interim communication director, Sebastian. Thank you.